Right, so hello to you all and welcome to Etteplan's Coffee Break webinars. Before we get started, we briefly introduce ourselves. Erin, would you like to start?
Sure. Yes. Hi, everybody. I'm Erin Comey, and I am an additive manufacturing specialist from Etteplan, and I have a bit of a varied background in engineering with 3 different engineering degrees in different fields. But for these last 5 years, I have been working on simulation and design topics related to metal additive manufacturing.
And my name is Tero Hämeenaho. I'm the department manager of Additive Manufacturing at Etteplan. I have been in the engineering business over 16 years for now and later years heavily in additive manufacturing. But before we go into today's topic, very briefly about our company. So Etteplan is an engineering service company with over 3,500 engineers and 3 service areas. So we have engineering solutions, software and embedded solutions, and technical documentation services. In the field of additive manufacturing, we are one of the forerunners in Nordics. And over the years, we have gathered a lot of knowledge from this new technology, and I'm pleased to host a set of webinars with my additive manufacturing experts. Last week, we had a webinar on how to find suitable AM applications, and the second webinar focuses on design. And in the coming weeks, we will dig into the cost of additive manufacturing, and from there we will go into an industrialized AM production, trying to lead you through the whole process. I also want to give thanks to the co-organizer for this webinar, Tampere Fairs, that help us to share the message of these webinars. We were originally meant to speak about these topics at the 3D and new material fairs at Tampere in March. But since these extreme times and the coronavirus, we are also very pleased that we are able to share our message via these webinars. But now I will give lead to Erin. Please go ahead.
Okay, thank you, Tero. And welcome again, everybody, to this presentation on the use of simulation and also advanced 3D modeling within AM design. Before I get started, I just wanted to say that if you have any questions during the presentation, please feel free to type them into the question section on the right hand of your screen in the control panel where it says questions, and we will try to answer as many of those as possible at the end of the presentation. And to get us started today, I wanted to show you the 2 key guiding principles that Etteplan is using when it's coming to AM projects. The first one of these is essentially our AMMO team motto, and that is that added value comes from design. And so basically the reason why we are saying this is that in order to take full advantage of the geometric freedoms that AM offers us, we need to design specifically for this manufacturing method. And for this, we prefer to use simulation and advanced 3D modeling to design for function and for performance as each case might dictate. This second principle is shown on the right here, and it's the idea that we need teamwork or close cooperation with our customers, our mechanical design engineers and simulation experts within Etteplan, and the network of print service bureaus, machine manufacturers, powder suppliers, and so on, in order to achieve a successful AM design. And so within this, with this in mind, today I will discuss some of the people or areas of expertise and the tools that are needed for AM design in general, and then go over 3 customer cases where I will describe how we put this into practice. So let's start by taking a bit of a closer look at our typical AM design workflow. We start out each case by working very closely with our customers to create a good business case, and then to also review all of the starting data that we have for a given project. Then we typically start this iterative process of ideation and concept creation. And once we have a final concept or concepts that are chosen, we move on to the detailed design phase of the project. From there, this is followed by final design validation, and then we deliver the geometries and the drawings to our manufacturer. And so for each AM design project, we need to start this whole workflow by assembling the appropriate team of people and working out what simulation and modeling tools will be needed to complete the job. So here's a look at some of the key roles or fields of expertise that we often find in our AM design projects. And as I mentioned earlier, we'd like to work closely with our end customer. So quite often there's a product expert that is included in our design team. We also need a strong understanding of the AM method or technology and the needed post-processing for that technology, as well as relevant material data and a design approach for that particular AM method. We also work closely with the structural, thermal, and fluid dynamic experts on our engineering analysis team. So they're doing, for example, the FEM and CFD simulations for us. And finally, we almost always include someone who is simulating the actual printing process in these projects. And now let's take a look also at some of the simulation and design tools that we're using. So to start out with, we have finite element analysis and computational fluid dynamics. This is often used at the beginning of our design projects to evaluate a structure or fluid flow in the existing design. And then it's also used throughout the entire project to guide our new designs and ensure in the end that we're meeting all of the performance targets. We're also using topology optimization and generative design, usually early in the design process, to optimize the use of material for known or assumed loading conditions. And then we're using advanced 3D modeling, and we use this to try to take advantage of these geometric freedoms offered by additive manufacturing. And so, for example, this might include using lattice structures or bionic design to add new functionality or reduce weight of the product, or it allows us to use the information gained through the earlier FEM or CFD simulations to create a more optimal structure. And finally, we use print process simulation to guide us to find, for example, the best part orientations on the build platform, to create and to optimize support structures, to predict recoater blade collision and other possible build failures, and to estimate distortions and stresses and so on in our final product. So here's a list of some of the software tools and for both design and CAD and also for simulation that are currently available, or actually these were available already last year. And what we have seen is that while there are dedicated tools specifically for AM design and simulation, these are being updated constantly with new features and more players coming to the market seemingly every day. So now that we've taken a brief look at the needed team and the tools that we're using for AM design, I thought we could take a look at some real design cases to see how this works in practice. So the first case that I wanted to show today is a hydraulic block that is brought to us by John Deere Forestry. And so the hydraulic block, which you can see on the right of my screen here, is positioned on the boom of a tree harvester. And the main design goals for this particular project were to, one, try to decrease the pressure drop in the hydraulic block. Because it's located on the boom, it was also hoped that we could reduce the weight. And while doing so, they wanted us to minimize the manufacturing costs and try to make the part to help ease assembly and disassembly of this and the surrounding components. So here I have shown the design approach that we took for this case, and what you'll see is on the right hand of the slide, I included a summary of the expertise that were needed within the design team, as well as the tools that were utilized. And if you go back now to the left side of the screen, you can see that for this particular case, The design of the hydraulic block was driven by the optimization of the internal channels. And so we used computational fluid dynamics to evaluate the flow and the pressure drop in the original design. And then all of the channel concepts that we came up with at the beginning of the project were then evaluated as well with CFD. From there, a final channel concept was chosen based on a combination of the lowest pressure drop and also printability. And this was done by having close cooperation between our AM design expert and our CFD analyst. And then from there, once this final concept was chosen, there were more fine-tuning done to further improve the performance of these channels. Once we had the channel design set, then the next job was to sort of create the body of the hydraulic block, and this was designed then around those channels. After the initial or the first iteration of this component design then was ready, we started to use finite element analyses to look at the strength and the performance of the new design. And it was also used to help us to optimize the wall thickness throughout the entire part and to determine the location and dimension of needed rib structures during the final fine-tuning of the design. Then at this stage, we used print process simulation, and that was used to help position the part on the build platform, analyze the needed support structures, and to guarantee that they were strong enough that this part wouldn't lift off the platform during the build, and to basically guarantee the printability of the part. By working this way, we are able to achieve quite a number of benefits in this additive manufacture design. We were able to create a very unique channel geometry that reduced the pressure drop of the part by 40%, while still being printable and working well with high velocity flow in both directions, which was important for this part. We were also able to reduce the mass of the component by 60% and have an overall size reduction that allowed for easier assembly and disassembly of the surrounding parts. Next, we have a tooling case that came to us from Wärtsilä. And this component, which you can see on the right, was part of a pressing tool assembly meant for the installation of cylinder head valves for one of their new engines. And initially, this part was meant to be machined and then welded, as you can see in white and black figure on the bottom right of this slide. But after FEM analysis of this design was conducted, they deemed that it would be unsafe for use. So they came to us and asked us to redesign this part for AM quickly, because basically they needed it yesterday and within a set manufacturing budget. So for this case, topology optimization was used to guide the design, and because we wanted to both optimize the use of material and also create a self-supporting structure that would minimize printing and post-processing costs. And again, I've listed the team of experts and the tools that we used for this case on the right hand of the slide. So after we had done the initial topology optimizations, we used finite element analysis to evaluate those optimization results, and then again later on to ensure that the final component design could be used safely. We also used advanced 3D modeling for this project, and that was essentially to interpret the design variation that we chose from our concepts generated with the topology optimization and create this final structure geometry. In the end, once again, we used print process simulation, and for this case, it showed that the part could be printed as designed and with very low distortion levels. And so the benefits here that were seen from taking this design approach included having a design ready and to the manufacturer in less than 1 week from the time that the customer set our starting data. And we are also able to keep the manufacturing costs within budget because we optimized the use of material and also created this self-supporting structure. And finally, we have a safer design that was ready to use for the installation of these cylinder head valves. And now we can move on to our final case, which is coming from Mirka. And this case is a dust extraction channel used for a robotic sander. And the original part you can see there on the right. And this project started with Mirka actually identifying this part as one that they felt that might benefit from additive manufacturing because it was expensive to make. It's a rather small part, and they only needed 1,000 of these per year. And so they wanted Etteplan to redesign the part to take full advantage of additive manufacturing, hoping that the end product would be lighter, have significantly better airflow characteristics, be better looking, and most importantly, have lower manufacturing costs. And now this was a component in a high-end product. So while it's not actually subject to significant loads, it still needed to be made out of metal, and then it would eventually be coated with, after printing to be matte black. And so the aim here was to make this better looking component with the costs reduced enough that Mirka could move the production back to Finland. So this case is a bit different than the previous two that I have shown in that the design was not driven by finite element analyses or computational fluid dynamics, but instead by the costs. And so for this case, we started out by using our own Etteplan cost estimation tool, which you'll hear Johannes tell a little bit more about in the webinar next week. And anyways, this tool was used upfront to create the business case for this part with the customer before any of the design work was started. And so with this cost estimation tool, we saw that if you were to print a part of the size that was estimated, if you print only one piece at a time, the cost of that part would be more than 6 times the traditional manufactured part. If you were to print 11 of those parts in a single build job, then you would have the break-even point. So the cost would be the same per piece as it is to manufacture now. And then we saw that as you print more of these parts in a build, the price continues to fall. And so with this information, we saw that there could be significant cost savings and some manufacturing flexibility if we were to design the part so that it could be stacked during printing. And so with this sort of guiding our design, we moved to our AM design expert who started first by designing the internal channels to make them nice and smooth, and then building the part around or building the rest of the structure around those channels. We used print process simulation early and often for this particular case. So early on, it was used to check the first design iterations for printability. And then as the design progressed, we used it to determine the optimal print orientations. You can see in the image in the top right, there's 2 orientations of the part being shown, and those were actually the 2 that were optimal for printing. And so then basically we took those 2 orientations and started to design the part for stacking based on those. Print process simulation then was used again to help determine where support structures would be needed during stacking and to ensure that the full stack would print successfully. And also to check that the distortion levels are not varying significantly between parts on the bottom of the stack or those on the top. And so with this stack design and the support strategies in place, we were able to start planning this, the full build. And so with this design approach, we were able to print 150 of these dust extraction channels in a single build on an SLM 280. And so with this fully nested build job, we were able to reduce the costs by 40%. But then we took this one step further by going to SLM Solutions and working with them to optimize the process parameters and therefore reduce the printing time and costs by an additional 25%. So with these cost reductions, Mirka is now able to move the production of this part back to Finland. In addition, we were able to exceed the customer's expectations by creating a part with a better surface finish and overall appearance, these significantly better airflow characteristics, and also a 58% reduction in weight. So before we move on to the end of this session where we start answering some of your questions, I wanted to take a quick look at how these Etteplan coffee break webinars will be continuing. And so as Tero mentioned earlier, we have 2 more sessions coming up. So next Friday, May 8th, we have Johannes Karilainen, and he's going to talk about the cost of 3D printing. And he will be showing this cost estimation tool that I mentioned in this Mirka case. And then the week after that, Henrik Tolander will be talking about the industrialization of additive manufacturing. And so with that, I think now we can move on to this question and answer portion of this webinar.
Thank you, Erin. And for the audience, if you have any questions related to design in overall or simulation-driven design, please go ahead and you can use these questions place. Okay, we can already see now I can already see that there is a questions. So let's start from those ones. The first one is can parts be hardened after printing? And yes, they can. With the different post-processing methods, you can influence the material characteristics of different additive manufacturing materials. Erin, would you like to take the second one? The question was, is there a deviation between metal AM process simulation and actual results? If yes, then how you compensate it?
Sorry, I'm having trouble reading the questions, and so can you ask one more time?
Yeah.
Apologies.
Is there a deviation between metal AM process simulation and actual results, and how you can compensate it if there is?
Well, yes, with all simulation, I guess you can say that there's always some deviation between the reality and the simulation. And so I think the best way to do that is, I guess it depends on the method that you're using, but definitely use measurement and validation practices to go back and check where simulation and the reality are deviating. And I think it's more or less a continuous process to try to have the best possible definition, like within the simulation tool of what is actually happening, but then also to continuously check that everything is right. I can answer, if you have more specific question about that, I can also try to answer more later on as well.
Then we had a question, did you use any post-processing method to decrease the porosity of the hydraulic component, and how about the surface roughness on the inside of the pipes? So yes, there was certain post-processing methods and heat treatments using that component. We cannot say what were used, and about the surface roughnesses in this case, there is a different certain honing made for the component. Do you always need to purchase a new tool for design simulation, or do you have all-in-one software available? Would you like to, Erin, take that one?
At the moment, we do not have one like a single all-in-one design software available. So like I was saying, there's a lot of different tools on the market, and they all, I think many or all of them have really good features, but we have found that within our AM workflow, for example, for the CAD design, people have preferences about which tool that they want to use there. And then for simulation, I think it depends also on the expert and the case involved. So at the moment, we don't have an all-in-one tool that we're using, but we are using several. And at the same time, this is something that we're currently studying and basically checking what's coming to the market, what can we use for what case, but yeah, it's really case dependent, I could say.
Yeah. Then we have, can the process simulation limitations be considered during the FEM or topology optimization?
Process simulation limitations or build limitations. So during topology optimization, for example, we can consider like the build orientation and try to guide the design to be self-supporting, if that's what you mean. But during topology optimization, I think we have not been able to consider, for example, distortions during the build. I don't know if there's any tools that allow you to do that, if that's what you had in mind. And then if you're talking about with finite element analysis, maybe you're talking about stresses after the build. I think, I'm not sure if there's any tools that allow you to make that loop going from, you know, the print process simulation and directly take. I know you can get the stress state after the build and then consider that back in your finite element model, but I don't know if there's the direct loop for that sort of thing at this point.
Yeah. Then we have that what kind of post-processing was used for the stacked part and how much of the total part cost was post-processing. It was sandblasted and then painted afterwards to get the better surface roughnesses, and because there was like print time optimization made for that part, it made the part surface a little more rougher at certain part of the component, but then after sandblasting and painting, the surface is really smooth. And I cannot remember the actual post-processing cost, but the actual savings shown that one included the post-processing cost.
Yeah, and I could add one more thing, that actually SLM also optimized, SLM solutions, that is, optimized supporting structures for that case. And so the support structures were extremely easy to remove. So you could basically peel them off by hand really easily. So that didn't take a significant amount of time.
Yeah. Which softwares are you using for the process simulation?
At the moment, we're mostly using Additive Works Amphion. So it's an inherent strain method tool, but we've also been testing several other products as well.
Does the surface roughness of the printed parts negatively affect fluid flow?
It affects fluid flow, but not necessarily negatively. I think it's one of those things, we always say this with AM products, but it depends. And I guess it really is case dependent, and it depends on the size of the channels and the orientations during printing and the type of surface roughness you're getting. But it's definitely something that should be taken into consideration during the CFD and design of internal channels.
Yep. What is the estimated parts amount when this kind of stacking, like in Mirka case in AM printing, it starts to be a cost effective? Well, in Mirka case, Erin said that the break-even point was somewhere in 11 pieces, but in metal printing, like Johannes will tell more about the cost and what affects into it, but the volume and how much parts you can fit into a build, they have a significant factors for cost, but we will come back to that on coming week. Have you printed heat exchangers? Is it feasible? We are working with few projects with heat exchangers, and it's feasible, and you can have a quite good benefits within those ones. But pretty much, if you consider the printer, for example, normal plate heat exchanger, no point of doing that one. You need to design them differently and trying to get some added value from printing. In case 2, advanced 3D modeling, is it inspired by the topology and remodeled?
Yes, definitely. So with that case, we ran quite a large number of the topology optimization cases because we were considering 3 different materials, and we were including different manufacturing constraints in the topology optimization, and had some variations in our design space. And so once we chose the actual basic design that we wanted to go with, or the basic iteration that we were happy with, then we used, actually we took 2 approaches. We did one version using PTC Creo, and then also we did one version using these polynerves in Solid Thinking Inspire to basically follow the optimized geometry and then create this final sort of organic looking solid that we used and then printed.
Yeah, but in some cases, like I said, we can start to like smoothen the result of topology optimization and thinking how the build starts with and how to avoid support structures, and then in some cases we can just try to like throw on top of the topology result with some other software tool.
Yes, and to a certain extent, this is becoming more and more automated. I mean, I remember trying to do this exact same task 5 years ago, and it might take days to basically interpret a topology optimized result. And now you can get a pretty reasonable result almost automatically after the topology optimization, and in some cases totally acceptable to go straight to printer depending on what you're doing.
Is it possible for a mechanical engineer to do a topology optimization, or do you need to have an engineering analysis expert?
I think that there's different levels, and actually the tools have been created so that there's usually a version for advanced simulation expert, and then there's a version for mechanical design engineer. And so the version for the mechanical design engineer might not give you as many different loading options, or like you might not have the same options with different types of boundary conditions or dealing with contact or this sort of thing. But yeah, I think basic static loading, you can definitely do topology optimization, and actually most or many of the main CAD tools offered by the big software vendors or houses now have definitely have topology optimization included or have it as an add-on.
How well do you think that the simulation tools present the actual printing process? Have you noticed that there might be a problem points in the build during building that the simulation tool did not predict?
Yes, definitely. I think it depends on the material and that you're using and the process. And for example, if you're using inherent strain method, it depends also on for example, the type of structures that you're building and so on. Or if you're using one of these other methods, it may depend on how well you have defined, for example, these temperature-dependent material properties and these sort of things. And so, yeah, I guess it definitely depends. And of course, if you have errors in the simulation, it's not going to match perfectly. But I think with regularly, checking and validating those simulations, then we do the best that we can to avoid that. And I think that we're also using the print process simulation like early and often to get an idea of where we might have problems in a design. So to give some indication of where, for example, we have really large distortions that might give us a problem later on. And by doing that, the simulation doesn't have to be perfect, but it just needs to give us sort of like this relative idea of, you know, here we have no distortion and here we have massive distortion. And so in that area, you might want to make some small design changes.
Then how did you compensate the spring back of wrapping in Mirka case, warping?
We didn't do any design compensation for the Mirka case because the distortion levels were deemed low enough, and yeah, so the printing was done with the original design without any sort of compensation.
In the first example, you changed manifold structure to a 3D printed structure. How does this affect the cost and manufacturing times? Basically, within hydraulic blocks, it's quite hard to achieve cost reduction. If you think about the starting point where there were a stupid block of metal that had direct drills, so those are pretty cost effective to manufacturing as they are. So in that case, the business case comes from replacing many blocks in a component, and through that one you can have a process savings, and you can affect to multiple different places in that whole product. But still, it's like really hard to have like a similar cost level, for example, in hydraulic blocks, when the starting point is really cheap. Good. If no other questions, I will thank you all for joining our webinar. Really nice questions, and hopefully we'll see you all in a coming week to hear more about additive manufacturing and learn more about the cost effect of printing. Thank you for my behalf.
Thanks, everyone. Bye.